Hello friends, in this video I will explain how to solve a problem on one-dimensional bar element. In this problem, the bar element which I have considered is a stepped bar and it is made up of two different materials having different properties. The problem statement is like this. An axial load P equal to 200 kN is applied as shown in the figure. Calculate nodal displacements, stress in each element, reactions at the support or reaction forces. I will take the diagram. I will explain about this one. This is the stepper bar as given. At the left end, extreme left end, it is constrained, that is fixed, and at the right end also it is fixed. And you can observe that at the right end there is an arrow mark and written as X. It shows that right side direction is assumed positive direction. Any force acting opposite to this one, that we have to consider it as negative value. Okay. And a load of P equal to 200 kN, that is acting where there is cross section is changing. Now we will see that the length of the element which is made up of aluminum, that is 300 millimeters, and length of the another element which is made up of steel, that is 400 millimeters. Write down all the given values, and he has also given cross section area of the both the elements here. A1, there is cross section area of element number 1, 2400 millimeter square. Similarly, A2 is 600 millimeter square. Young's modulus E1 equal to 70 into 10 to the power of 5 Newton per meter square. I will convert this one into Newton per millimeter square because all the dimensions what he has given is in millimeter square. So I convert this value also in terms of millimeter only. So that becomes 70 into 10 to the power of 3 Newton per millimeter square. In step number 1, I will draw a FEA model of the bar element, that is line diagram of the bar element. In this one, I have to represent all the node numbers, and node numbering I have done starting from the left side. At the extreme left side, I have taken as node number 1, and the place where the cross section area is changing, I will consider this as node number 2, and extreme right side I will consider that node number 3. So between node 1 and 2, that is element number 1, between nodes 2 and 3, that is element number 2. Now, and displacements, Q1 is the displacement at node 1 and F1 is the force acting at node 1. Similarly, Q2, Q3, F2, F3 are the values at node number 2 and 3 respectively. Step number 2, elemental stiffness matrix. The general equation for finding the elemental stiffness matrix of bar element is like this. K equal to A1 E1 upon L1, 1 minus 1 minus 1 1. This is for element number 1. That's why suffix 1 I have used for all the rotations. Where K1, in general K is the stiffness matrix. K1 means that is for stiffness matrix for element number 1. And A1 is the cross section area of element number 1. E1 is the Young's modulus of element number 1. L1 is the length of element number 1. So 1 minus 1 minus 1. This is the matrix. The whole together that is called as elemental stiffness matrix. Substitute all the values. That is A1 2400 millimeter square, E1 17 to 10 to the power of 3 Newton per millimeter square, L1 300 millimeter square. Calculate this part, A1 E1 upon L1, that comes as 0.56 into 10 to the power of 6. For calculation purpose, for making easy for us, what I will do, 0.56 I will multiply inside, 10 to the power of 6 I will keep outside the matrix. Now whatever the term we are keeping outside the matrix, that should be same for the next stiffness matrix also. Then only it will be easy for additioning. Here, see here, 10 into 10 to the power of 6 I have taken outside, 0.56 I have multiplied inside. So K1 becomes 10 to the power of 6, 0.56 minus 0.56 minus 0.56, 0.56. And here I have written as column and row numbers 1 and 2, because for element number 2, you can see in the FEA model, for element number 1, nodes are 1 and 2. That's why row and column numbers I have to write as 1 and 2 for first element. Similarly, find out the stiffness matrix for element number 2. The question remains, stiffness matrix equation remains same, only values are going to change here. A2 is 600 millimeter square, E2 2 into 10 to the power of 5 Newton per millimeter square, L2 400 millimeter. Calculate this one, it comes as 0.3 into 10 to the power of 6. Here also, as I told already, 10 to the power of 6, same thing I have to take outside here. Remaining term is 0.3, that I will multiply inside. Now K2 becomes 10 to the power of 6, 0.3 minus 0.3 minus 0.3, 0.3. Row and column numbers are 2, 3 here, because you can see in the FE model, for element number 2, the nodes are 2 and 3. That's why the row and column numbers are 2 and 3 here. Next step is finding the global stiffness matrix. That we will get by adding these two stiffness matrix, that is K1 and K2. So K equal to global stiffness matrix, K equal to K1 plus K2. This addition procedure is very, very important. This, what I will do to make it very easy, what I will do, I will write a matrix of 3 cross 3. Outside I will take it as 10 to the power of 6, because after adding this term remains common. That's why common term I will write outside first. Now right now that matrix is blank inside. Only row and column numbers I have written outside. 1, 2, 3 they are column numbers. 1, 2, 3 they are row numbers. Why up to 3 only? Because the nodes, the maximum nodes for this element are 3. So size of the global stiffness matrix becomes 3 cross 3. Now inside, how to write the inside values after adding? See here, you have to check row wise and column wise. See, for example, in column number 1, row 1, in that place, what I would write? I have written here 0.56, because come back to K1 and check it. At column 1 and row 1, the value is 0.56, this one. That's why here I have written as 0.56. Similarly, here row 2, column 2 and row 1, I have written as minus 0.6. Similarly, check here also. Column 2, row 1, that is in K1, that value is minus 0.6. That's why I have written as minus 0.6. Column 3, row 1, here I have written 0, because that place, column 3 and row 1, we won't get in both the matrices, K1 and K2. That's why that value I have written as 0. Similarly write column 1, row 2. But when you come to the column 2 and row 2, there I have written as 0.86. Here, this value, column 2, row 2, we will get in the both the matrices K1 and K2. See here, in K1, in the place of column 2, row 2, I have 0.56. In K2, in the place of column 2 and row 2, I have 0.3. The two values are coming in the same place. That is, one is 0.56, another value is 0.3. So I have to add these two. After adding, I am getting as 0.86. In this way, I have to add this one. Similarly, write column 3 and row 2. Write down all the values like this. Then you will get global stiffness matrix. Next step. Global displacement vector Q equal to Q1, Q2, Q3. These are the displacements at node 1, 2, 3 respectively that we are going to find now. Next, global force vector, or we can call it as also global load vector also. F1, F2, F3. F1 is 0 because no force is acting at node 1. F2 equal to 200 into 10 to the power of 3. This is given in the diagram. We can see here. at node 2 where the cross section is changing, P value is given there in the question, P equal to 200 kilonewton. That's why P equal to 200 into 10 to the power of 3 Newton. F3, at node 3 there is no force, that's why F3 is 0. Now, very next step is step number 6. Very important is assembling or equilibrium equation. That equation is KQ equal to F. You know K, you know Q, you know F. Substitute there. That equation is like this. Next is step number 7, applying boundary condition. This is very, very important. Here there are two approaches. One is elimination approach, or more is penalty approach. This problem I am solving by elimination approach. Elimination means we have to eliminate particular row and columns from this equation. This equation means the equation what we are getting in step number 6. That is equilibrium equation. Which row and which column we have to eliminate? That is our question. That we will come to know by understanding one sentence. Wherever the displacement is known, or a node where you know the displacement, that particular row and column you have to eliminate. For example, in this problem, node number 1, that is extreme left side, it is completely fixed. So we won't find any displacement in that place. That is Q1 equal to 0. At node 1, displacement is known for us, that is 0 now. Hence eliminate first row, first column. Similarly, at the extreme right end, that is at node 3, there also it is fixed. Here also displacement will be 0. Here also we know the displacement, hence eliminate row 3 and column 3. That we can see here in this step number 7 we have done. See here, row 3, row 1 eliminated, column 1, column 3 also eliminated. Only thing we should check that wherever the displacement is known, that particular row and column has to be eliminated. Now remaining terms we can write down in the form of equation. The remaining values are 10 to the power of 6. You should not forget that will be outside, that you have to multiply, then you have to consider inside value. 10 to the power of 6 into 0.86 into Q2 equal to 200 into 10 to the power of 3. These are the remaining terms that I have written. So calculate this equation, solve this equation, we will get Q2. Okay. Q2, that is the displacement at node 2 is found now. Now Q1 is known, that is 0. Q2 we found now 0.2325 millimeters. Q3 that is 0. So all the displacements we found now. First part of the problem is over now. Next part is in finding the stresses. To find the stress, the general equation is like this. Sigma equal to E upon L minus 1 Q1 Q2. Why Q1 Q2 here? This is for element number 1. So for element number 1, nodes are 1 and 2. That's why Q1 and Q2. Substitute the values, calculate. We are getting as sigma 1, that is stress in element number 1 as 54.25 megapascal. Similarly, sigma 2. Here E2 upon L2 minus 1 Q2 Q3. Here I have taken Q2 and Q3 because the nodes for element number 2 are 2 and 3. That's why Q2 Q3. Calculate this one. We are getting it as sigma 2 as minus 116.25 megapascal. Using penalty approach I have written here. You neglect this one because we are solving this problem by elimination approach. That's why this part we will consider when we start solving with the penalty approach. Next, I will take the third part of the problem, that is finding the reaction forces. For this, the general equation is R equal to KQ minus F. Here I have not written that equation. We will come to know R. R means reactions, K means stiffness matrix, Q means displacements minus F. F means load vector. Here first I will multiply these two matrices, that is K and Q. Whatever the answer we are getting, that I will subtract with the next matrix, that is force matrix. Now finally we are getting as answers as R1, R2, R3 as like this. These values we are getting. Now in this way we have to find reaction forces also. This is the third part of the problem. This is the method how to solve the problems on one-dimensional bar elements. Thank you.